Welcome everyone. So this is a conducting polymer part 2 lecture. In the part 1 we discussed about that what is conducting polymer, what is the origin for conductivity in the conducting polymer, different types of conducting polymer, intrinsically conducting polymer, extrinsically conducting polymer, based on the composition, how different conductive polymers can be classified. And also we talked about the some of the conducting polymers such as polyacetylene, polypyrrole, polythiophene, etc. And also we talked about the applications of conducting polymer, how the N-doping and P-doping conductivity of the polymer can be enhanced. So in this segment, in this lecture, we'll talk about the in-depth analysis of P-doping and N-doping of polymer, what is the mechanism, and some of the examples of N-dopants and P-dopants. And also we'll select some of the conducting polymers such as polyacetylene, poly-3-hexylthiophene, their synthesis, properties, applications, etc. So these are the contents we'll touch upon in this lecture. So in the previous lecture we talked about the intrinsic conducting polymer and extrinsic conducting polymer. So what is the intrinsic conducting polymer? Where the conducting polymer, the conductivity is inherent in nature. So the conduction of electricity in this type of polymer is due to the conjugation in the backbone of the polymer. As we know that there is alternate single bond and double bond, and the available p orbital which are orthogonally directed contains one electron each. Due to the delocalization of pi electron, the conductivity takes place. So the conjugation is mainly due to the pi electrons or the doped ingredients. Intrinsic polymers with conjugation. In this type of polymer, because of the presence of double bond or lone pair of electron, conduction of electricity takes place. So in this case, we are not adding any dopants. We are not adding any ingredient from outside. This is very inherent type in nature. The examples are polyacetylene, polyaniline, polypyrrole, etc. But whenever we add some dopants, the oxidation of the backbone or reduction of the backbone takes place, and therefore there is a creation of positive charge or negative charge in the polymer backbone, and that leads to the enhancement of the conductivity. So these are referred as doped conducting polymer. So doping process are also two types, N-type doping and P-type doping. As I said that the doping can be of two types, P-doping and N-doping. What is P-doping? When the polymers are treated with oxidizing agents such as Lewis acid or halogens, the oxidation of the polymer backbone takes place, and therefore there is a creation of positively charged sites in the polymer backbone. So they are acting as a good conductors of electricity. It is called P-doping or oxidative doping. The examples of P dopants are iodine, bromine, aluminium chloride, AsF5, ferric chloride, etc. So all these dopants are electron deficient. So when they are treated with this polymer, they can take the electron from the polymer. So that's why the oxidation takes place, and positive charge is being created at the backbone, and that is the reason for enhancement of the conductivity. So this is called p-doping. And in n-doping, so when the polymers are treated with Lewis bases or alkali metals, so the reduction of the polymer takes place, and therefore negatively charged sites are being created on the polymer backbone. So these are called n-doping or reductive doping. So what are the n-dopants? Sodium, potassium, lithium, naphthalides. When they are treated with conducting polymer, they transfer the electron to the polymer backbone, and therefore the reduction takes place. As a result, there is a creation of negatively charged sites, and which leads up to the enhancement of the conductivity. So that is called n-doping or reductive doping. So we'll talk about the synthesis of conducting polymer, and also we'll talk about that how p-doping and n-doping takes place in the conducting polymer. That means the mechanism. So we all know that polyacetylene is a conducting polymer. How it can be synthesized? It can be synthesized due to the polymerization of acetylene in the presence of Ziegler-Natta catalyst. So it undergoes the addition polymerization, and therefore gives rise to the two types of polymer based on the spatial orientation. One is the cis polyacetylene and another is trans polyacetylene. So this is a structure of trans polyacetylene which has an alternate single bond double bond character. So this is infusible, insoluble, and becomes brittle on exposure to air. And the intrinsic conductivity is due to the presence of single bond and double bond, etc. Further, if we add p-dopants or n-dopants, the conductivity increases. So when the polyacetylene is treated with iodine, oxidation takes place. So iodine can take up the electron from the polyacetylene backbone chain, and therefore the oxidation takes place. There is a creation of positive charge in the backbone, and that is the responsible for the enhancement of the conductivity. So we'll talk about the detailed mechanism of p-doping of polyacetylene, and the conductivity of cis polyacetylene is less than trans polyacetylene. When we see the p-doping of conducting polymer, so it undergoes into 3 steps. So what are the steps of p-doping? So as a total, there are 3 steps of p-doping: step 1, step 2, and step 3. Step 1, when the polyacetylene is treated with iodine, oxidation takes place to produce a delocalized radical ion. It is called polaron. So this is a step 1. Further, in the step 2, this polaron again interacts with the same iodine. Therefore, the further oxidation takes place, and it produces 2 positive charges carrying on the polyacetylene chain. It is called bipolaron. Why bipolaron? Because 2 radical ions are produced in the chain and they are nearby. In the final step, what happens that these positive charges are moving in the opposite direction and hence responsible for electrical conduction because of delocalization. So basically, in the step 3, whatever the 2 polarons are created, they are moving in the opposite direction through delocalized pi orbital, and eventually it produces soliton, and that is responsible for electrical conductivity. So schematically, if we try to explain the p-doping, so this is the polyacetylene backbone, And when it is treated with iodine, what happens that oxidation takes place in the polymer backbone. For example, there is a double bond here, there is a homolytic cleavage takes place, and this carbon acquires one electron, this carbon acquires one electron. This electron further is given up to the iodine. Okay, so that created this radical ion. So here this carbon, there is a positive charge, and this carbon, there is a radical. So this is called as a polaron. This is a first step. Further, whatever the electron is there in this carbon, this can be given up to another iodine molecule. So this is a second step of oxidation, and thereby it creates two positively charged ion on the two neighboring carbon atom, and the counter ion is I3 minus. So this is called bipolaron. So bipolaron is basically nothing but the created positively charged ions in the polymer backbone. And these two positively charged, when it will migrate in the opposite direction in the polymer backbone through the delocalized pi orbital, then the conductivity takes place. So when these two charge migrate in the two opposite direction, that creates soliton. So first step is the creation of polaron. The second step is oxidation takes place is a bipolaron, and third step is the soliton. Similar in line of p doping, we can talk about the N doping of polyacetylene. N doping means if we add N dopants, that leads to the reduction of the polymer backbone, and thereby it creates the negative charge in the polymer backbone. And the created negative charge can migrate to the polymer backbone. So here, when the acetylene is treated with the sodium or potassium naphthalate, the reduction takes place. Here it is a sodium naphthalate, so we can identify as a B. It also involves the three step. In the first step, when it is treated with sodium naphthalate, the electron goes to the polymer backbone. That means a reduction takes place, and therefore there is a creation of radical anion. So this is called polaron. So this is the first step of reduction. The second step of reduction, another electron goes from the sodium naphthalate to the polymer backbone, and therefore it creates the two negatively charged sides in the two neighboring carbon atom. So that is called bipolaron. So this is the second step. And in the third step, what happens that these two negatively charged sides, the negatively charged can migrate in the opposite direction through the polymer backbone with the help of delocalized p orbital, and that creates the soliton. So that is why the conductivity enhanced. So this is the mechanism of N-doping of polyacetylene, and it also involves the three-step similar in line with p-dop polymer. So the enhancement of conductivity can be explained from this schematic diagram and with the relative position of valence band and conduction band. So this is a polyacetylene neutral chain when there was no dopant added. So whatever the conductivity, that is due to the alternate double bond and single bond. And this is the scenario where the relative position of valence band and conduction band, and this is the gap between the valence band and conduction band. Whenever we add dopants, either p dopants or n dopants, what happens, there is a intermediate levels are being created between the valence band and conduction band. So these are like polar ion bands between the valence band and conduction band. And therefore, ultimately, it will lead up to the soliton band when the two charge can migrate in the opposite direction of the chain, and that leads up to the soliton. And when there will be many more solitons, it will create a soliton band. So this band is located in between the valence band and conduction band. So because of this intermediate soliton band, the electron can easily percolate from valence band to soliton band, and further from soliton band to conduction band. In this way, the conductivity of the polymer can be enhanced. In the previous slide, we talk about the n-doping and p-doping of conducting polymer, and in this slide we will talk about some of the selective examples of conducting polymer, such as polyacetylene, poly-3-hexylthiophene. So how they can be synthesized, their property and their application. So these are the aspects we'll talk about. So first example is polyacetylene. Polyacetylene, we all know, it can be synthesized starting from acetylene gas via addition polymerization with the help of Ziegler-Natta catalyst. So this is basically a rigid rod-like polymer and consists of long carbon chains with alternating single and double bonds between the carbon atoms, and that attributes to the electrical conductivity. So this was discussed by Hideki Shirakawa, Alan Heeger and Alan McDermott, who received the Nobel Prize in Chemistry in 2000 for their work. Again, if we see the structure of polyacetylene, there can be the two polyacetylene. One is cis polyacetylene and another is trans polyacetylene. Cis polyacetylene is copper colored and trans is silver colored. You can see that depending upon the orientation of double bond, this can be either cis polyacetylene or trans polyacetylene, but both consist of alternate single bond and double bond, and it has been observed that trans polyacetylene has more conductivity than cis polyacetylene. Preparation of polyacetylene. So polyacetylene is a polymer and the building block or monomer is acetylene. So this acetylene undergoes addition polymerization in presence of Ziegler-Natta catalyst, and it can lead to the two types of polyacetylene depending on the structure. It can be cis polyacetylene or trans polyacetylene. If the temperature is maintained minus 78 degrees Celsius in presence of toluene, it undergoes addition polymerization and therefore it generates cis polyacetylene, which is copper colored. And if the reaction is being carried out at 150 degrees Celsius in hexadecane solvent, then it generates the trans polyacetylene, which is silver colored. Further, if the cis polyacetylene is heated beyond 145 degrees Celsius, the reorientation takes place and it leads to the trans polyacetylene. So trans polyacetylene is more stable than cis polyacetylene, and also because of the regioregularity and the orientation of the double bond, it has the more conductivity compared to the cis polyacetylene. So we have seen the synthesis of polyacetylene. So what are the properties of polyacetylene? Films of cis polyacetylene are flexible and can be readily stretched. while trans polyacetylene is much more brittle. Both cis and trans polyacetylene show high thermal stability. And number 3, they are insoluble in common solvent. So these are the general properties of polyacetylene. And if we talk about the applications, because application is due to the alternate single bond and double bond and the electron delocalization through the p orbital, and further the doped polyacetylene offers a particularly high electrical conductivity. Therefore, it can be used in electric wiring or electrode material in lightweight rechargeable batteries. And number 2, triiodide oxidized polyacetylene can be used as a sensor to measure glucose concentration. Disubstituted polyacetylenes can be used in the detection of alpha amino acids, etc. So these are some of the important applications of polyacetylene. Another example is poly 3-hexyl thiophene. So poly 3-hexyl thiophene, the monomer unit is 3-hexyl thiophene. It contains heteroatom containing aromatic moiety, and the heteroatom is sulfur. So sulfur lone pair and these two pi bonds involved into the conjugation. And also in the 3 position, this hexyl group is attached. So this polymer has received much attention in the field of electronic devices, including organic field effect transistors, organic photovoltaic cells, and it is one of the best types of balanced high performance material used as a p-type semiconductor in terms of solubility, chemical stability, charge mobility, and commercial availability. And also, because it is treated as p-type material, it can be blended with any other n-type material such as PCBM, and that can be used for organic photovoltaic cells. So this is about P3HT or poly 3-hexyl thiophene. Now we'll see the preparation of poly 3-hexyl thiophene. What are the synthetic methods for the preparation of poly 3-hexyl thiophene? There are several synthetic methods starting from the halogen substituted monomer. So the main preparation techniques involve the nickel catalyzed cross coupling reaction in presence of Grignard reagent, starting from the halogen substituted monomeric unit. And through this Grignard metathesis polymerization reaction, this polymerization takes place and therefore it leads up to the poly 3-hexyl thiophene. And also there is a synthetic procedure where there is a dehydrogenative polycondensation reaction takes place in presence of catalyst starting from the monomer, and this output depends on the concentration of monomer as well as the temperature. So basically we can see that it can lead to the head to tail regioregular poly 3-hexyl thiophene preparation with this temperature, and this method is very effective method. That means the nickel catalyzed cross coupling reaction in presence of Grignard reagent. So this can generate up to more than 98% poly 3-hexyl thiophene. So if if we see the stepwise mechanism for preparation of P3HT, as I said before, that it involves the nickel catalyzed cross-coupling reaction in presence of Grignard reagent starting from the halogen substituted thiophene monomer. So what happens here? If we treat with the monomer with this nickel catalyst, this nickel catalyst is embedded between the two monomeric unit, and then it will walk through polyconjugation, walk through the conjugation, and it will transfer from here to here. So basically it will go here. Okay, so therefore the coupling takes place between this monomer unit with this monomer unit. Because the nickel transfer through the conjugation, therefore it leads to the coupling reaction. That is referred as transmetallation. So when the nickel is transferred here in this position, it can add up another monomeric unit. And again, through transmetallation, it will go here. It comes in between this carbon and bromine. So this is how the condensation coupling takes place, and tail to tail orientation, this polymerization is carried out. Ultimately, when the chain terminates, it is treated with 5-molar hydrochloric acid. So it will cleave this carbon nickel bond. So that ends the polymerization. So this is the stepwise mechanism for the preparation of P3HT. In the previous slide, we discussed about the synthesis of P3HT. Now we will talk about the properties of poly-3-hexylthiophene. P3HT exhibits excellent electrical conductivity, making it suitable for application in organic electronics. P3HT has electroluminescent properties, meaning it can emit light when an electric current is applied. It also has non-linear optical properties. Further, it is highly soluble in chlorinated solvents such as chloroform, chlorobenzene, dichlorobenzene, trichlorobenzene. It is also soluble in non-chlorinated solvents like xylene, toluene, THF, etc. P3HT can have a high degree of regioregularity, which refers to the arrangement of repeating units in the polymer chain. Her regioregularity is desirable for better performance in organic electronics, because due to the higher regioregularity, the electron percolation through the backbone is facilitated, and thereby the conductance increases. So that is why for conducting polymer, regioregularity is very essential parameter. What are the applications of poly-3-hexylthiophene? P3HT is used as a donor material in organic photovoltaic cells, absorbing light and generating an electric current. P3HT has electrolumination properties, meaning it can emit light when an electric current is applied. This makes it useful in OLEDs. It is also used as a semiconducting material in organic field effective transistor, where it can be used to control the flow of electric current. P3HT can be repurposed as a conductivity reducing additive for polyethylene based high voltage insulation. It can be used as a conductive binder for lithium-ion battery cathode materials, where it offers advantageous properties such as high electronic and ionic conductivity and suppression of electrolyte breakdown. So we discussed in this lecture the p-type and n-type conductivity of the polyacetylene, their mechanism, and how the positively charged or negatively charged site enhances the conductivity. And we discussed about the three-step enhancement: polaron, bipolaron, and eventually soliton. Then we selected two conducting polymers, polyacetylene and poly-3-hexylthiophene. We talked about their synthesis, properties, and application. With this, we'll conclude this session, and we talked about the conducting polymer. Thank you all.